There are a variety of possibilities to investigate resonant motions caused by eigenperiods in AquaSim. You will be introduced to how they can be calculated explicitly, and how they can be investigated in broader sense. Eigenperiods are also commonly referred to as natural periods, or eigenfrequencies. We apply the term eigenperiod through this video. These types of periods are important in the sense of understanding the response of structures. It is determined by the distribution of mass and stiffness. Resonant motions can cause significant response in the structure, and in worst-case failure of structural integrity. One classical example of resonant motions causing structural failure is the Tacoma Narrows Bridge in the USA. When wind was passing across the bridge, strong oscillating movements was registered on the main span of the bridge. The phenomenon gave the bridge its nickname, Galloping Gertie. At its worst, the bridge moved 1.5 meters up and down and tilted 45 degrees with a period of 5 seconds. The motions escalated until the main span eventually collapsed. Eigenperiod analysis is available through a built-in tool, found in the Export menu. Scroll down to the Advanced section, until you find the buckling eigenperiod analysis. By selecting the checkbox and then 3 dots to the right, one enters the control window for eigenperiod settings. Let us explain some of the parameters. Analysis type tells us if we want to conduct an eigenperiod or a buckling analysis. For eigenperiod there are 3 different choices, and the main difference between them is whether the mass of truss and point loads are included or not. Trusses and point loads can generate numerous of eigenperiods, which, simply put, can be perceived as noise if they are not an essential part of the problem you are investigating. Then you have a choice to exclude them from the analysis. The eigenperiod analysis solves this equation, where K is the stiffness of your structure, and M is the mass. The result that is found is the eigenvalue omega. The amount of eigenvalues written to file must be a number between 0 or 7. If this parameter is equal to 3, then the 3 eigenperiods closest to shift value is calculated. Analysis is valid for, gives you the opportunity to select whether nonlinear material relations should be accounted for. Having conducted the eigenperiod analysis, some additional files will be generated. If you have chosen to set amount of eigenvalues written to file equal to 6, you will get 6 additional files. The first file, eigen1, includes the results for the eigenperiod that is closest to shift value. The eigen2 file contains results for eigenperiod second closest to shift value. And so on. Please note that each step in the analysis is considered separately, such that you must evaluate each step. Let's proceed with some practical examples. For this example, you may apply the AquaSim model called barge, that is associated with this tutorial. These are found online on our documentation center. This is a typical barge applied for storage of fish feed and equipment in the aquaculture industry. It is approximate 45 meters long, 12 meters wide and a draft of 2.6 meters. The barge has mass and added mass due to displacement of water fluid. The barge has a main hull, and a deckhouse with a bridge. It is moored with 8 anchor lines, 2 in each direction. So, why is it of interest to investigate eigenperiods of moored barges? The forces in the anchor lines are dependent on slow drift motions. If these motions coincide with the natural period of the barge and anchor line system, one can risk large escalating forces. The stiffness in the anchor lines is nonlinear, meaning that the eigenperiod of the system will be different depending on the displacement of the barge. We should now investigate the eigenperiod found from stiffness and mass. To do so, one must introduce displacement to the barge. This is done by applying wind on the broadside of the barge. This corresponds to a long Y direction. The wind will induce forces in the anchor lines, because of the barge displacement. The eigenperiod is then found based on the displacement and the net horizontal force in the anchor lines. Go to the Export menu and select the Prepare tab-side wind. A wind velocity of 40 meters per second is applied. We should now export the model and run an analysis. Open the result file that ends with .avz. We should investigate the horizontal displacement and forces in the anchor lines. Select Result, Displacement, and Displacement Y. Click on an element on the main hull of the barge. Wind is applied in incremental steps, meaning that it is linearly increased from zero to fully developed through the initial steps in the analysis. The displacement from step 1 to 11 is noticed and copied to a table. The net horizontal force is found through selecting global section forces and force Y. Results for each anchor line is copied to a table where the net horizontal force is calculated. Then tangential stiffness K is found. F is the net horizontal force, and R is the displacement of the barge. The eigenperiod is then found as 2 pi times the square root of mass over stiffness. Based on this, we get the following eigenperiods for motion along y direction. Here we have the displacement and net forces found from the AquaSim analysis, and the period is found from this, varying from 74 seconds to 55 seconds. Having found an estimate for the eigenperiods, we should apply the AquaSim eigenperiod calculation tool and compare results. Go back to your AquaEdit model and select Export. We choose the tab named Sidewind and scroll down to the Advanced section to the Buckling Eigenperiod Analysis. Select the checkbox to activate the Analysis tool. Then click on the 3 dots to open the control window. The chosen analysis type will account for the mass of truss elements when the eigenperiod is found. In our case, the anchor lines are modeled as truss elements. 6 eigenvalues will be written to file, and the amplitude of the eigenvector is 10. Select OK. Export the model and run the analysis. When the analysis is finished, open the eigen1 file in AquaView. Eigenperiods are found under Result, Results, and Eigenperiod. Click on an element in your model to view results. If we start the playback, we can see how the barge displaces. This displacement indicates the direction of the eigenperiod that is found. The first 7 steps correspond to the first eigenvector for translation along y-axis. The eigenperiods for the last steps correspond to another direction, more like surge. Take notice of the eigenperiods for the first 7 steps. Close this file, and open the next eigen file, the one that ends with the number 2. Select Result, Results, and Eigenperiod. Again, select an element on the model to display the eigenperiod. If we start the playback, we may see how the barge displaces. From this we can see that step number 8 to 11 will correspond to eigenperiods for translation along y-axis. The results from the 2 methods are plotted and compared in this graph. The eigenperiods match quite well, except from in the start. It appears that this is due to the stiffness, and the direct calculations becomes a bit smaller than the one based on mass and stiffness. This was 2 examples of how eigenperiods can be investigated for an anchored system. Another case where the eigenperiod is important for the structural integrity is wind turbines. For fatigue-driven structures, such as wind turbine, it is of importance to keep potential repeating forces, such as waves, away from the eigenperiods of the main structure. If the force-induced motions are close to the eigenperiods, the structural lifetime of the wind turbines may be reduced dramatically. In this case study we should see how structural parts affects the eigenperiod of a generic wind turbine system, and how the eigenperiod changes depending on static or dynamic considerations. We are considering 3 different configurations. The first configuration is with the turbine only. The second configuration contains turbine and the tower. The last case is turbine placed on a fixed jacket. The analyses are carried out such that the first steps, the turbine blades are stationary, meaning that they are not rotating. The last part of the analysis, the blades are rotating. Let us start with the eigenperiod analysis containing only the turbine, where we have selected the eigenperiod that is second highest. This is the eigenperiod where one blade is bending back and forth. The eigenperiods are plotted, and the playback is started. The 5 initial steps are considered static. The succeeding steps are then dynamic, meaning the blades are rotating. As one can see, is that the eigenperiod changes from the static part to dynamic. The centrifugal force due to blade rotation are influencing the geometric stiffness. The static eigenperiod is around 2.8 seconds. And the dynamic is about 2.7 seconds. Now, let us consider the results for the turbine placed on a jacket. The eigenperiod in the dynamic part is approximate 3 seconds. This is due to the stiffness of the system is reduced. This will contribute to a higher eigenperiod. Comparing all three cases, one can see that the eigenperiod is sensitive to stiffness of the full system. From the turbine-only case to turbine jacket, you can see the eigenperiod is increasing. All files presented here, and more, is available online at our website. Visit aquasim.no for more videos.